Right away, I want you to open your books to page 30 and complete this warm-up problem. Describe how to produce one step of the pattern from the previous step. Pause the video now and try this. All right, we're going to come back to that, don't worry. Lesson 1.5 is all about how sequences are functions. So the number of dots, d of n, is a function of the step number n. What values make sense for this situation? Well, if we're talking about those dots that I just showed you on the warm-up, n values that make sense, well, we don't have a step number 0, and we don't have negative steps, so n has to be greater than 0, positive, but we also don't have a half a step, or a quarter step, or 0.1 step. So n also has to be an integer. Remember, an integer is like a whole number, positive or negative, but we also said it has to be positive. Also think about what numbers don't make sense for n. We just mentioned those. Negative values, decimals, fractions, any non-whole value of n. So when we talk about our step numbers, going back to the warm-up still, right? Step 1, there's 1 dot. Step 2, there's 3. Step 3, there's 6. And step 4, there's 10. Hopefully you noticed that we add 2, then 3, then 4, which is actually the step number. So if we fill in this table, step 1 has 1 dot. Step 2 has d of 1, which is 1, plus 2, which is 3 dots. Step 3 has d of 2, which is 3, plus the step number 3, which is 6 dots. So step 4 should have the number of dots in step 3, so d of 3, plus 4, because it's step 4, which means 6 plus 4, which is 10 dots. So for step 5, we should take the number of dots in step 4, d of 4, plus my step number, which is 5. So 10 plus 5 makes 15 dots in step 5. Following the pattern in the table, we are going to write an equation for d of n in terms of the previous step. To do this, we take and write d of n, number of dots in the current step, equals the number of dots in the last step, or previous step, plus the step number. The way we write this out, the number of dots in the previous step is d of n minus 1. If d of n is the current step, n minus 1 is the previous step. So this says the number of dots in the previous step, plus my step number. Well, my step number is n. So there's my rule. D of n equals d of n minus 1 plus n. Is this sequence arithmetic, geometric, or neither? Explain. To do this, we take and check the rules we've learned about already. So to check for an arithmetic sequence, we subtract values. Any value minus the step before it. So let's take step 5 is 15 minus step 4 was 10. That gives me 5. All right, well, step 4 was 10 and step 3 was 6. That gives me 4. Already those differences are not equal, so we know it is not arithmetic. To be absolutely sure, we could keep checking, but I know that step 3 minus step 2 is not 4, and step 2 minus step 1 is not 3. None of these differences are the same, so it's absolutely not arithmetic. Let's check geometric. To see if it's geometric, we divide a value by the value before it. So I would start off with 15 over 10. Well, 15 over 10 simplifies to 3 over 2, or 1.5. And then we would take 10 over 6. 10 over 6 simplifies to 5 over 3, or 1.6 repeating. So already I can tell you those are not equal, so therefore it is not geometric. And just to be absolutely sure, we'll keep going. 6 over the step before it was 3, and 3 over the step before it was 1. 6 over 3 is 2, absolutely not equal to the others, and 3 over 1 is 3, absolutely not equal to the others. So it is not arithmetic, it is not geometric, which means it is neither. Because there is no common difference or no common ratio. Well, and no common ratio. We define this sequence recursively. The definition of recursively means defined using a repeated or recursive process for getting the values. You need to know what value to start at and what values n can be. Usually, we'll write n is greater than or equal to 2, because if we want to use the step before it, and there's no step 0, we can't start with the first step. D of 1 will always be the first term. Okay, 1 is the term number, D of 1 means the first term. D of n is the nth term or general term. Sometimes your directions will say, give me the general term. That means D of n. D of n minus 1 is just the term before it. Sequences are a type of function whose domain is a subset of the integers. Remember that domain means your possible input values. And integers are those positive and negative whole numbers. So I've got that domain is all possible input values. An important part of working with functions is defining a domain that makes sense in the given context. We will have to give our domain, such as n is greater than or equal to 2, and n is an integer. So let's define some sequences. Use the first 5 terms of each sequence to state if the sequence is arithmetic, geometric, or neither. Then define the sequence recursively using function notation. We'll do 2 of these together really quick before I have you try some on your own. So the first thing is to decide whether the sequence is arithmetic, geometric, or neither. Well, in this first one, I have 30, 40, 50, 60, 70. I notice that it's going up by 10 each time. We're adding the same value each time, so that means this is arithmetic. So D of n, you can change the D here. You don't even have to use n. You can just choose a different variable. I don't care. But any term will equal the term before it, so D of n minus 1. And then we said the rule is to add 10, so I say plus 10. So this means to get the third term, 1, 2, 3, to get 50, I take the term before it, 40, plus 10. That makes 50. All right, let's try this next one. 80, 40, 20, 10, 5, 2.5. Well, I take a look at this and I notice that the pattern is dividing by 2 each time. So I'll say that is geometric. Because remember, dividing by 2 means a common ratio of 1/2 or 0.5. So to write our rule, we'll say D of n equals the term before it, D of n minus 1, times 1/2 or 0.5. And there we have it. I want you to pause the video now and try numbers 3, 4, 5, and 6. All right, hopefully you've tried numbers 3, 4, 5, and 6 now, and we're going to talk about them. Number 3, you might notice that it's multiplying by 2 each time, so that is geometric. So we'll say D of n, any term, is equal to the term before it, D of n minus 1, times 2. Now, if you wanted to, you could also write 2 times d of n minus 1. Remember that multiplication and addition work that way, that you can flip the order around and it means the same thing. All right, for number 4, hopefully you saw that we're multiplying the denominators by 2, which means it is geometric because we're multiplying. So any term, d of n, is equal to the term before it times, well, we're multiplying the denominator by 2 and the numerator is staying the same, so it's multiplied by 1. We're multiplying by a half. For number 5, hopefully we notice the common difference is 7, but we're going down by 7. So this is arithmetic. So any term, d of n, is equal to the term before it, d of n minus 1, minus 7. And for number 6, notice that we don't add the same number each time, and we don't multiply by the same number each time. This is neither arithmetic nor geometric. Our pattern here is that we multiply by 2 and then add 1. So we can still write our rule. D of n is equal to the term before it, d of n minus 1, multiplied by 2, and then we add 1. Same exact thing as we were doing, just 2 steps. What did you notice about the sequences and rules we just looked at? Hopefully you noticed that geometric uses multiplication, and arithmetic use addition or subtraction. This gives us a very good rule. The recursive definition of a geometric sequence will always involve multiplication. The recursive definition of an arithmetic sequence will always involve addition or subtraction. And another very, very important thing will be to always note the first term. D of 1 equals what? We talked about this when we talked about sequences at the very beginning. You always have to give what the first term is. So really on all of these that we just did, we should go back in and say, all right, the first one, d of 1 was 30. The second one, d of 1 was 80. The third one, d of 1 was 1. Fourth one, d of 1 was 1. Fifth one, d of 1 was 20. And sixth one, d of 1 was again 1. Remember also that we should always state what n should be. For all of these, n has the same rule. N was greater than or equal to 2. We could use 2, 3, 4, 5, blah, 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 any whole number of n and make it work. So let's try to define this sequence formally. Use the first 5 terms of sequence H to define the sequence recursively using function notation. Well, I noticed that it's not a common difference, it's not arithmetic, and maybe it's geometric. Let's find out. I divide. So I'll show you what I'm dividing here. 202.5 divided by 67.5. How about 67.5 divided by 22.5? 22.5 divided by 7.5. 7.5 divided by 2.5. Look at that, I always got 3. That means it is geometric. We have a common ratio of 3. So sequence H, so my rule is just going to be called H of n. All I have to do is take the term before it, H of n minus 1, and multiply by 3. We note the first term, H of 1. We started at 2.5. And we also want to say that n is greater than or equal to 2, and n is n integer. This is the full definition of this sequence using function notation. So now you're just going to fill in a little summary. A sequence is a list of numbers. A geometric sequence is congruent to an exponential function. In a geometric sequence, you multiply each term by the growth factor. An example is 2, 6, 18, 54. The growth factor is 3 in that case. The recursive definition, f of 1 is 2, f of n equals 3 times f of n minus 1, and n is greater than or equal to 2. For an arithmetic sequence, or in a linear function, you're going to add to each term the rate of change. Our example here is 2, 7, 12, 17. The rate of change is 5. The recursive definition is that g of 1 equals 2 and g of n equals 5 plus g of n minus 1 for n greater than or equal to 2. So now you have your assignment that you can work on.